Hello everybody and welcome to Discussions in Orbit, REXUS BEXUS Edition, our series of live interviews organized by Team DROPSTAR. If you're familiar with DROPSTAR, you know that our team participates in the REXUS BEXUS Programme, a German-Swedish student program where teams from all over Europe are selected to design, build and execute an experiment in one of the two available platforms, BEXUS, which is a stratospheric balloon, or REXUS, which is a single-stage rocket. In Discussions in Orbit, REXUS BEXUS Edition, we interview fellow REXUS BEXUS teams in order for them to introduce their experiments to the public and share their experience in the program. So today's team is CREATE.
Team CREATE aims to gain an improved understanding on the influence of gravity on fiber matrix impregnation in additive manufacturing of composites. In the experiment, a material called polylactide or PLA is co-extruded with the carbon fiber. The nozzle temperature as well as ambient pressure and temperature are recorded. The experiment is conducted both in Earth and in microgravity conditions utilizing the REXUS rocket. A comparison of the two samples will show the influence of gravity on the fiber matrix impregnation and the material properties. So let's now meet the team behind the experiment. Hello, Team CREATE. Let's quickly introduce yourselves to the public.
Hello, thank you for the introduction. My name is Leonard. I'm the team lead of Team CREATE here from my office in Berlin. I just finished my studies in aerospace engineering and these are my colleagues Noria and Peter, and I would like them to introduce themselves.
Hi, my name is Noria and I'm currently studying physics in the master's degree in Braunschweig, and I'm working mostly on the science and outreach part of the experiment, but also do some thermal analysis and so on.
Yes, and my name is Peter. I recently finished my studies in information technology, and in CREATE I'm mainly working on the electronics and a little bit on software.
Great. Welcome, Team CREATE, to Discussions in Orbit. And we would like to start your interview with the most basic, as I say, questions. For you, we would like to describe the concept of your experiment.
Sure. So as you already introduced very kindly our experiment, the basic idea is to co-extrude carbon fibers with plastic filament. And the idea why we do this is to produce samples of higher tensile strength than plastic normally has by introducing carbon fibers into the material. And this co-extruding through 3D printing is quite a new concept in material science, and we want to help to better understand this process by investigating the effect of microgravity on this co-extrusion of these two materials. And to answer your question of the concept of the material, basic concept is we are building basically a 3D printer, similar to the ones you might have in your workshop or at home, shrink it down to the size so that it fits in a rocket compartment, fully automated so that it works without remote control in microgravity. And that's the basic concept, only that we instead of extruding only PLA, we co-extrude PLA and carbon fibers.
Well, that certainly sounds very interesting and also quite cryptic to the average person, I'd say, that doesn't really dwell in such issues. So would you be able to describe the science behind your experiment so that we can learn a bit more about it?
Sure. So the science behind our experiment is basically that fluids normally behave accordingly to the law by Newton, the law of viscosity, but molten PLA in microgravity does not behave like a Newtonian fluid, so it behaves like a non-Newtonian fluid, and that means that its stability increases. So when we want to insert a endless fiber into PLA or something else, you always need some interaction between the fiber and the matrix material. So the interface between those two materials should be as smoothly as possible so that there are no voids or cracks or whatever. And the behavior as a non-Newtonian fluid of the PLA increases the wettability of it, so that the possibility that voids form at the fiber matrix interfaces are much smaller than producing it like on Earth. So that's basically what we want to see if that is happening. So if the voids that form at the fiber matrix interface on Earth are smaller or even gone when producing the composite in microgravity.
Very interesting. And now that you have told us about the science of your experiment, I think we need to learn more about the technical characteristics of your experiment. How are you going to study this phenomenon? And what are the technical characteristics that make your experiment innovative and unique?
Yeah, so on the technical side, of course, yeah, we have the special challenges that we have to basically build a 3D printer for a rocket. So to reach this microgravitational environment we have and want to fly on board the rocket, that means we first of all have to build a 3D printer which is compact enough for the rocket itself. It needs to be fully automated because we can basically not interact that much with it during the flight. And yeah, also we have to deal with all the thermal challenges 3D printer brings with it, especially in a small chamber.
Yeah, and another main technical characteristic of especially our experiment is maybe that we have a sealed module. So the REXUS module that we are having our experiment in is hermetically sealed, so that we can keep a pressure of 1 atmosphere. So we're not changing any parameters besides the influence of gravity, so that we can have really look on the influence of gravity on the fiber matrix interface, and not also how pressure is changing and vacuum and so on. So that's also a very characteristic technical part of our experiment.
Well, it seems like you've got one of the challenging experiments in this REXUS rocket. And one can think of very many difficulties that you could have faced, but since we're talking to you and you can tell us firsthand, can you describe some of the most intense or most interesting difficulties that you've faced up until now?
Sure. As Noria just mentioned already, we have a pressurized vessel because, as Noria said, we don't want the influence of air or the lack of air better. We only want to test the influence of gravity. And the reason why, I mean, at first you might say, okay, a pressurized vessel, it's not that bad. People have done it times before. But the reason why this becomes a challenge is because we are in a rocket module with other modules above us and below us. So there needs to be some power lines, some communication cables, some GPS cables. There needs to be the cables that go to the nose cone to eject it and so on. And all these lines have to go through our pressurized vessel. So we have to maintain that pressure, yet at the same time having cables going through there. So this was one of the challenges. Another big challenge, I would say, is the power draw. Because we are on a rocket that has only batteries on board. We can't just plug it into a wall. We have to bring our power with us. Or the rocket brings the power, luckily for us. But we really have to take care that we can't draw too much power and just drain the batteries empty, so that all the other experiments don't have power anymore. And anybody who has a 3D printer might know that these machines consume quite a lot of power because they have this massive heat block that heats up to a temperature just by resistance, and this can draw quite a lot of power, so we have to limit our power draw, and one way we achieve this is by already heating it up before the launch, as long as the rocket is still connected to the ground support, and therefore we can draw power without draining the batteries. And then maybe a third quite challenging piece of our experiment is the extrusion itself. This co-extruding of filament with carbon fibers is a super new field of science. Currently, there are only a few machines who can do this co-extruding of carbon fibers and plastics at the same time, even on Earth. And now building this for microgravity environment is super challenging, and we invest quite a lot of time of manufacturing the parts and of optimizing the processes to then be able to automate this process in microgravity.
Great. So a lot of challenges, but you seem to handle them very effortlessly, I would say. So all of that leads up to the launch campaign. We have a countdown, it reaches 0, and the rocket is launched. What is the timeline of your experiment? What will be happening during the flight?
Yes, so like already mentioned, basically we fly a 3D printer. So in our experiment we do, our experiment pretty much resembles what a usual 3D printer does. So we need to heat up the hot end and the nozzle basically. We need to extrude the material, and we need to give it time to cool down. And so if we adapt that to our timeline, it basically looks like this. So before launch, Leonard already mentioned it, we need to heat up to a certain extent because we do not have enough power during the flight to completely heat up the hot end. So pre-liftoff, we start heating. After liftoff, and between liftoff and microgravity, I would say, we need to do the rest of the heat up. So this is also the time where we draw the most of the power. And finally, when we received the microgravity signal from the rocket, then the actual, hopefully magic happens. We start the extrusion process. So we start the co-extrusion of the fiber and the PLA, and also immediately cool it down via a fan and store it on a spool which is rotating in the experiment. And we do this up until the point where we lose microgravity, and after that we hope that we have enough samples collected to do a proper evaluation of it.
It seems like you need just about every type of specialty in your team, like a bunch of software, a bunch of science, thermodynamics, a bunch of engineering. So I'm guessing you got like a large disciple spectrum in your team. Can you tell us more about how many members you are and how you're organized?
So basically, we as the team behind Create are all members of the student association called ERIC. This is an abbreviation for Experimental Raumfahrt Interessengemeinschaft, which is German for loosely translated Experimental Rocket Student Association. And we, as the team Create, are only a part of this student association, and in total we have 11 members from super different backgrounds. So there's some physicists, there's electrical engineers, mechanical engineers, aerospace engineers, computer scientists, of course. So quite diverse in the educational backgrounds, and I think this is also one of our strengths, that we are able to combine so many fields into one project as a team.
Yes, you do need a lot of specialties for such a project. I think we know that ourselves, and I think that it is true for every space experiment. And I would like to know, what are you currently working on?
Yeah, so it was not that long ago that we had our IPR, the Integration Progress Review. It was actually in the end of May, and there we were asked to mainly demonstrate our electronics and our software. So up until that point, we worked on finalizing the design and make it able to actually demonstrate the functionalities of our experiment. And now after that, we are basically working towards the integration and bench test week, which will be probably in the end of the year in December. And that means, we are basically finalizing components. So for the mechanical construction, we are doing now the last details basically, and we also start the manufacturing of actual flight hardware, so that we can bring it to Munich then to the shaker test. On the electronic side, we are also about to order the final versions of our PCBs, so they are now tested and are hopefully ready to be installed in the experiment. And of course, one big thing is the software. So of course we need reliable software. Without software, the experiment won't run, and this will now be finalized and tested.
Sounds like you've. I'm sorry. Please continue.
All right. Another part of our team is working hard on producing samples with our prototype, so that we can do some preliminary tests to see what tests we're going to perform on the samples after the flight, and what are the material properties that we can compare, or which are interesting to be compared. And therefore, one challenge that we're facing right now is how to insert the fiber in the hot end so that it won't ripple or break or get stuck or whatever, so that it comes out in a nice line. So that's another part besides the software and the electronics what we're currently working on.
And actually, I want to add one more point, which shall not be remain unmentioned. We are also working currently on 2 papers. We submitted 2 abstracts to the IAC in Baku, the International Astronautical Congress. And one of the papers describes the technical construction of our experiment, and one is focused on science. And both abstracts were accepted, and we are now actually writing papers.
Yeah, before you said that, I was gonna say you've done a massive amount of work. Now I don't know exactly how to describe it.
Yeah, we need to congratulate you on the papers as well.
Right. Well, yeah, you're doing this work and you're also making the most out of it, which is excellent. And it seems like you've done the largest amount of work, I would say, before coming to a campaign. So, since we've been through the largest part of the timeline for the REXUS campaign, I would like to ask you, what was your experience so far? How would you describe it?
So I think that I can speak for all of us, that our experience so far was very good. So it was very teaching to work with those experts from ESA, SSC, TSAM, and DLR. We had a lot to learn from them, and it was also very interesting to meet the other teams to see what they are performing, what experiments are going to be with us on the rocket. And then also another very interesting part was to actually work on a more or less real space mission, so to see how it is actually working on a space mission, what is very interesting, and what are the points which are there to be considered and to be thought of when we're talking about flying an experiment on a rocket and then performing the experiment in microgravity. So there are a lot of things that you have to think of, and those were one of the experiences which were very helpful so far.
Also, I want to mention that originally we thought that the REXUS time would already be over 3 months ago, but due to COVID and all this, we had a prolonged duration for the cycle of REXUS. So I think we actually enjoy it, that we have the time to like go even deeper into our technical parts of the experiments, but also working together as a team is great. So I think the experiments can be summarized as quite positive.
Great. And with experience, I think that the self-evaluation follows. So you also mentioned that you had to think about a lot of things with your experiment and you learned a lot of things. So I would like to know, what do you wish you knew before you started your journey on REXUS BEXUS?
Who would like to share that?
Yeah, one experience and yeah, one thing we wish we would have known is that yeah, how hard and important it is to yeah, to gain new members during such a long period of a project. So especially for a student association like we are, and like probably all of the REXUS teams are, people come and go. Of course, people finish their studies and so, and especially due to that additional year, it was quite important for us to always look out for new people. And there was a time where we realized that, but it could have been a little bit earlier, to be honest. That was one thing.
I think another thing that is to be mentioned is how important it is to prototype. I think by now we have got the idea, and we are actually prototyping quite a lot. But this is something I over and over experience again and again, that prototyping is the most important bit. So you have to really build components of your experiment, be it as small as you want, but you have to like iterate over and over to really learn and come to the point you want to reach. So that's why I was laughing before when Peter was mentioning that we are just ordering our final PCBs. I know already we are probably going to order 2 or 3 more, but it's always good to have the mentality to say, okay, this is now the final one, but then final comes after, and then final B2 and so on.
Yeah, those creative namings for either file names or the actual models. So now that we're done with the past, I'd like to bring us back to the present. And since you've gone all the things that you've gone through, and since we've spoken about things that you wish you knew, or you believe that it would make your life easier to know, I'd like to learn what you actually believe you learned through this entire process. What things you believe you've taken so far with you.
So speaking for me, I've learned a lot about the process of space mission design and what points to think of. And another very important thing that I took from the REXUS project so far is that even if you don't have anything to do with the topic or you don't know anything about it, it doesn't matter. You can learn everything and you can familiarize with everything, and you have in a team, you have people besides you who can show you how something is working, who can show you how to manufacture parts or how to build something, how to draw a CAD model or whatever. So don't get stopped by the idea that you don't know enough about a project or about, well, actually anything. Because once you start it, you'll find the way and you'll see how it goes. And you learn everything about what you need to know to fulfill your task and to work on the project.
Right.
Yes.
Is it possible that we get an answer from each of you?
Yes, of course. So for me, yeah, like I said, I work mainly on the electronics and software, and it was kind of already mentioned, but I really want to emphasize that it's really important to do practical tests as early as possible. So it's one thing to design everything, and maybe even another thing to simulate stuff, but only when you really try out things that you thought about, then you will really learn if stuff works. So yeah, we already had a laugh about it, but every time I ordered a new iteration of the PCBs, I was like, wow, if it goes well, this is flight hardware, and it never was. So yeah, start that process early, do prototyping, manufacturing, testing, and then you have a realistic chance of actually building a working experiment in the end.
For me, personally, this was the first real project where I was as a project manager instead of as an engineer. So I, of course, learned a lot about that. For example, when doing financial budgets, I learned, okay, it's always more expensive than you think. But at the same time, what I also learned is how kind other companies can be. So we reached out to some institutes, to some companies, and they were actually very kind in sponsoring us and helping us with this endeavor. So this is definitely one lesson learned. I would say that it is always worth to reach out to ask for help if you need help, and most of the time you will get help. Similar to what Noria also said, but I mean also in a professional context with other entities other than your team colleagues.
Very interesting. Thank you for your answers. And to close this interview, I would like to ask my personally favorite question, because we can see the passion of the team members. What will be your experiment's contribution?
So as we already mentioned in the beginning, 3D printing with fibers, carbon fibers inside, is a very new field of in terms of the 3D printing. So we will also help to understand and improve the carbon fiber reinforced 3D printing processes. So we'll see how gravity is influencing the process of additive 3D printing, and therewith we can also contribute to someday printing on the ISS or in space. I mean, they are already manufacturing in space, so there are some experiments on that already, but not with the carbon reinforced, as far as I know. So our experiment will contribute to that we can understand the influence that microgravity has on the impregnation process, and therefore we have an increased sustainability in terms of being able to produce or manufacture parts which are needed on a space station directly or in space by a satellite or whatever. So that's like in the future somewhere, but we're already contributing to that. And also we have an outcome for production with additive manufacturing on Earth, because when you know how the material properties of the carbon reinforced plastics behave when you're producing in microgravity, you know the different influences, you know more about the process, you're able to create a broader range of products so that we can produce more with 3D printing and not only the stuff that we know so far.
Well, we wish you all the best. And Team Create, we would like to thank you for being with us in Discussions in Orbit. Thank you for participating. and we hope that everything goes well with your experiment.
Thank you
Right.
very much.
Thank you so much for the interview. I think it's really great that you take the time to interview all the experiments. This is a really great platform, and thank you for the interview.
Well, see you on the rocket.
See you on the rocket.
Yeah.
See
Bye-bye.
you.
Bye.